Okay, let's take just a few minutes to summarize everything we've learned in the Pivot Ping Pong Cannon lab that we just completed. Let's start by defining some of those basic vocab words. Most of these we've talked about in the lab, but there are a few ones that might be a little bit new. Now, the first word we want to take a look at is the word position. For position, we use the symbol small x. X marks the spot, and it wears a little kind of half arrow hat over it, which we'll talk about in a minute. And the position of an object is simply the location of that object at a given moment in time relative to some frame of reference. Okay, we've got to have a position measured from something. It could be the position from a starting line. It could be the position from directly north on a map. Or it could be the position in the x direction on a coordinate axis system. So basically, to have a position, you also have to know where your origin point is. Where are you measuring that from? What's your reference point? Now, because of that, position is what we call a vector quantity, which means that a position not only has an amount, it's 5 meters, it has a direction. It's 5 meters in this direction. It's 5 meters to the north, or it's 5 meters from the starting line, or it's 10 meters on the x-axis in the x direction. So there's always got to be, with position and many other quantities in physics, there's always got to be an amount, a magnitude, and a direction. When we have that kind of quantity that has to have a direction along with its amount, we call that a vector. And whenever we talk about quantities like position that are vectors, we make sure that we mark them with a little hat. And you can see that little hat right there. It's a little half arrow that just sits over top of the variable. So if you see a variable that has that little arrow on top of it, that means it's a vector quantity, which means if you want the right answer, you're going to have to provide an amount and also the direction that an object is, let's say, moving in or positioned at. Now, we have vectors and we have scalars. A scalar is a quantity that doesn't have a direction. It doesn't matter what direction you're talking because there isn't one that makes sense. And so a scalar only needs to have an amount in order to fully describe it. You either have some or you have none. And so in, the case of what we're going to be talking about in this lab, velocity is going to be a term that's a vector. Speed is going to be a scalar. Mass is a scalar. You either have mass or you don't. You can't really have negative mass. Energy is a scalar. You either have energy or you don't have energy. And so you don't have energy to the north. There's no direction that goes with that. Important for you at this point to define vector and scalar and be able to recognize the difference. Vectors wear a hat, scalars don't. And we will learn a lot more about vectors as we go through the rest of the course. Now, the basic difference between distance and displacement. Distance we represent with a small d, and it's simply the length of the path taken by an object that moves. It's the path length. It's like if we could take a measuring tape and just stretch it out, follow all the little curves and changes in the direction that the path takes, and measure up the length of that path exactly, that would be the distance. So in this situation with our biker here, as the biker starts and winds their way through here to, let's say this is their ending position, starting position, that path length is the distance. And this is a scalar quantity. We don't care about direction. We don't care if it changes direction. We don't care how many loops and curves and edges and corners, and we don't care how. what direction they take. We only care about the length of the actual path they travel. Now, displacement is something a little bit different. If this is the initial position right there at that dot, and this is the final position here at that dot, then the displacement is simply the straight line length between, it's hard to draw a straight line, between the final position and the initial position. It is the change ultimately of the object's position after the motion occurs that we care about. And so we use the symbol delta x for displacement. And remember, delta means change in, x means position. So this, when we look at delta x, we read that the change in the position. And remember, position is a vector quantity. It has both a direction and a magnitude. So displacement is also a vector quantity. It always has to have magnitude and it needs to have a direction, okay? Now, the distance and the displacement can be very, very different from one another. Let's say, for example, let's say we have a car, okay? And the car is right there at that dot. Let's say the car drives a great big loop and comes right back and stops exactly where the car started. The distance of this loop might be 1 mile long, let's say. However, the displacement would be 0. And that's because the final position is exactly the same as the initial position. So when you take final position minus initial position, you're going to get 0. Now, does that mean the object didn't move at all? No, the object moved and went the whole way around the circle. It did cover a certain distance in a certain time, therefore it did have a speed. But we would say here that the displacement would be 0, and this has dramatic consequences for what the velocity of the car would be. Now remember, velocity and speed are not the same thing, okay? Remember, speed is just how fast you are traveling. It is how fast an object travels a given path length in a certain amount of time. So speed, which we use a small little s for, speed is a scalar quantity. It doesn't care about direction, so it's just how fast are you going, okay? Velocity, though, is the rate of change of the object's position. This is how fast an object moves from one position to another position, regardless of the path it takes to get there. And velocity is a vector quantity. So velocity, a little v, wears a vector hat. We always write that little hat over top of it. And it is a vector. Now, this means that in our previous situation there, let's remember we had that car that went on a big long loop and came back and ended exactly where it started. The speed of this would be something, okay? It's how fast an object travels a given path length. Let's say it took, an hour to do that. The speed here would be 1 mile per hour because it took a mile-long path length in 1 hour. The velocity, however, would be 0, which is very counterintuitive. Why would the velocity be 0? Because the displacement is 0. It's the rate of the change of an object's position. Well, this object didn't ultimately change its position. It came back to exactly where it started from. The final position was equal to the initial position, which means that your displacement is 0 And it doesn't matter how long it took, ultimately, there is no velocity as we calculate velocity and define it. And so it's super important that we learn to use the word distance and displacement, or path length and displacement, and that we learn to use the word velocity and speed correctly at the right time, because they have some serious consequences for exactly what you're looking at in a physical situation and how you would go about solving a problem involving path lengths, distances, displacement, speeds, velocities. Now, one of the main goals of our Pivot Lab was to gather data, plot a graph, and then we did a linear fit on that graph. And we actually were very happy to let Pivot calculate out the slope of the line that resulted. And it gave us the y-intercept. It gave us some other information too that we didn't have to calculate. But remember, in our conversation after the lab, we did talk a little bit about what that actual graph meant. First of all, we were looking at what's called an XT graph, or a position time graph. And if you remember, we have our independent x-axis variable, that's time, and we have our dependent or responding variable on the y-axis, and that's going to be position, which in our case is an x. And that's why we call this an XT graph, okay? X on the y-axis, t on the x-axis. And if we want to calculate the slope of a straight line on that graph, then we know from our basic geometry or algebra classes that we use rise over run, which is the change in the y variable divided by the change in the x variable. So in our case, that would mean it would be the change in the position of the object divided by the change in the time of the object. And in our lab, we already talked about this, and we defined that as the velocity. And so the slope of this line is the velocity. And that means that the velocity of an object can be found using the equation for the slope, which is the change in the position of the object divided by the time, or the displacement of the object divided by time. So now we know that the slope of an XT graph is the velocity. I want you to put this on a little piece of paper, and I want you to stick it to your forehead. I want you to look at it. I want you to write it on your hand. I want you to memorize this. I'm going to ask you over and over again, where do I find velocity on an XT graph? It's the slope. The slope of an XT graph is the velocity. That is where you find it. You don't even have to do the math a lot of times if you have the graph right there, because a lot of times the slope will be easy to just kind of look at, or the slope itself on the graph will be given to you, and they're just trying to find out if you actually know how to use it. So remember, the slope of the graph gives us the velocity. The magnitude of the slope, the amount, how steep the slope is, that's the speed, okay? So that's the speed is simply one part of the velocity, okay? The sign gives us the direction, whether it is positive or negative. And we will talk a lot more about that as we go forward. What does that really mean? Because in any given problem, we're going to have to figure out or define for ourselves which direction is the positive direction, which direction is the negative direction, and then it will make sense. And we talked about the y-intercept of our graph. That y-intercept gives us the initial starting position. We mark that with an x little sub I or an x little sub O, either way. I'm trying to switch. I've always used xi sub I but I need to switch to X sub O because that's what AP uses. And I just need to get everybody all on the same page, but I'm struggling because it's hard to learn a new little thing when you've used one thing for 40 years. So, yeah, anyway. So you can use those interchangeably. Whichever one is fine. They mean the same thing, okay? They are the initial starting position. So what can you read off of an XT graph? You can find the velocity. It is the slope. You can figure out from that slope what direction the object is moving in and how fast it's moving. You can find out its original starting position. There's a lot of information right on that one simple little straight line graph. Now, we also are going to be doing a lot more as we go forward with velocity time graphs. These are graphs that have time on the independent axis, and they have velocity as the dependent variable, okay, on the y-axis. And here we usually show positive as up and we show negative as down on that, and then we see our x-axis kind of shooting off toward the right there in the middle, and that's our 0 line. Now, what can we tell from a velocity time graph? We can tell a lot. First of all, the slope of this graph gives us the change in the velocity, and we haven't talked about this or defined it or anything like that, but it basically tells us, is the velocity changing over time or is it staying the same? If you look at this graph at 1 second, here's the velocity. It's 10, positive 10. At 2 seconds, there's the velocity. It's still at positive 10. At 3 seconds, positive 10. This velocity is not changing, and the slope is equal to 0. For constant velocity, which is our first unit here, the slope of our VT graph will always be 0 because we're only looking at objects that are traveling with constant velocity, where the velocity is the same at every moment in the object's motion that we're looking at. The sign of the velocity gives us the direction, okay, that the object is moving in. Is it moving in the positive direction? Is it moving in the negative direction? In this case, we have an object with a positive velocity of 10 meters per second. So it's traveling in the positive direction at 10 meters per second. The y-intercept is going to give us the initial starting velocity. Again, that's going to be VI or VO. Both mean the same thing. I'm trying to switch myself over to all the sub-knots, the little V sub 0. And one very important trick here, very important trick. The area under a VT graph, and that's that shaded area I've just shaded, that gives us the displacement. And we're going to learn how to do this more. But if you take a look at this graph, if I want to know what is the displacement of this object in the first 2 seconds, then I can kind of look at this area right here. And what is the area? That's a rectangle. What's the area of a rectangle? It's length times width. The length of this is 2 seconds times the height or the width, whichever way you want to talk about that. That's 10 meters per second. Notice that seconds cancel and I end up with 20 meters. That is my displacement. It is super fast and super easy and a lot easier than some other options that will come our way. So always remember that the area under the curve or the line gives us the displacement, and that displacement is delta x. And finally, when we talked after the lab, we took the basic velocity equation from the slope of the xt graph and that was velocity equals the change in position divided by the change in time. And by expanding that and rewriting it and rearranging it a little bit, we can actually get a very helpful little equation. I just call it the position equation. That's not anything everybody uses or anything. But it helps us find an object's position if we know the initial starting position, velocity, and the time, the moment in time that we care about, which we often do. And so this is a very helpful, just rearranged writing of the velocity equation that is a quick one to learn. You must memorize this equation. I would suggest memorizing that one as well. You must memorize the velocity equation. For those of you in AP Physics, you are not even given that equation on the AP form. Okay, the formula sheet there, it's just considered too basic. So you'll get more complex equations given to you, but it is assumed you know this. So when I ask you at any point in the future, hint, hint, write down the equation for velocity, you should be able to do that without thinking, looking it up, or anything. Start yourself a little paper or an index card or little flashcards or something. Start yourself a formula sheet and put these two on there. But definitely this one. You just have to know it, okay? All right, we have learned a lot, and now let's see what we can do with all of this information.